So in the last class, I think there were a few doubts raised, and I think I'll just make a quick revision of the problem, and then we'll clear the doubts, and then we'll go ahead to the main agenda of this particular video. So what we were trying to do really is saying that, look, I have a simple pendulum, and I have some idea of how it moves. What if I write all the equations that I can write about the simple pendulum from whatever I have learned till now? And we have, I must say, we have a lot of things we have learned. So first thing is that it goes in a circle. That's good. The second thing is that when something goes in a circle and the radius is constant, now in this case we call the radius L, we know that there is a radial instant if you at that instant the radial acceleration is equal to L omega t at that instant, instantaneous angular velocity square. And now there's also a tangential acceleration, and somehow I imagine the object falling down, and I did not use any sign convention. So I'm going to address the sign convention in a minute, but what I did last time, I'll just try to quickly rephrase. And I said, look, there's going to be, I just assume that the pendulum is on the way down, and it's got a tangential acceleration, and that happens to be L alpha at that instant of time, okay? And we wrote down the two formulae. So these are the formulae that we know from the kinematics. Now next is we consider the forces. Now the forces are mg and t. And upfront, let me tell you that the main point I was really trying to say is that when we use everything that we know, we are also actually able to pin down Mr. T, which is right now an unknown. That really summarizes the main goal. Okay, so how did we go about it? So we said, look, at that instant maybe the displacement is theta, okay, and then we said let's resolve the forces. Let's freeze time. Now this is a very nice and simple idea. Let's freeze time, and so everything is frozen in time, and we analyze at that instant of time. So at that instant of time, let's actually choose the coordinate system, and that's the confusing part. I just chose the coordinate system along the I mean into the center and perpendicular to the center. So this is 90. So when you did this, we got an equation which said the force towards the center is T. Now this angle happens to be theta, and therefore if you resolve mg into component like this and a component like this, then this dotted line is mg sine theta, and the adjacent component is mg cos theta. And so pointing in, I think the arrows, I've got the arrows right. I think this is very important. The arrows are right, and the arrows do indicate away from the center. So therefore we have force towards the center is T minus mg cos theta is equal to mass. I think I made a typo last time. Mass into acceleration, which is L omega square t. So this is one equation. And what else did we do? We wrote down the other equation, which is and I must say that I disregarded the sign convention. I just said m. I mean, assuming that the pendulum is coming down and it's sort of accelerating. So mg sine theta is equal to mass into acceleration, which is L alpha t. And then we cancel them. So this is the summary of what we achieved last time. And what I said is, once your math gets a little better, you will rewrite this equation as mg sine theta at that instant of time is equal to L into d square of theta by dt square at that instant of time, and this is the same as this, and this is solvable. So that's what your math is going to tell you very soon, and therefore you'll get theta as a function of time is now known. Now many of you wrote to me saying that yes, this means that I know omega t, and that's very nice, because you just have to differentiate theta. So okay, what you guys were pointing out is that omega is equal to d theta by dt, and that's like very easy. Now what this means is that you know omega, and please, I think I should highlight this. What this means is that you know omega at that instant of time, and then all of a sudden, of course, you know theta at that instant of time, and therefore you can tell me t at that instant of time, and that's a major achievement. If you can tell me t at every instant of time, and I think that's the end of the story. So there we go. We are able to tell you what is theta at every instant of time. We're able to tell you what is omega at every instant of time. Alpha at every instant of time is definitely very easy. It's right here. It's right here. And then, I mean, right here if you want. And finally, I think the final statement is yes. What about t at every instant of time? So all the achievement of the physics we have studied, and that is a good summary. Okay, so now I think I should pay attention to what you guys have been now telling me, that pay attention to the sign convention. Okay, that's very important, by the way, and let's do the sign convention now. But now that you're comfortable with the fact that we're doing Newton's laws, then you are comfortable with the equations that I write, which are, by the way, let me just finish this in a jiffy. So if you have you take some starting point as the origin, and I'm talking about rotation now, and you measure anti-clockwise. So theta anti-clockwise, by convention, if you go in the anti-clockwise direction, then theta is positive, and if you go in the clockwise direction, then you say that theta is negative. So when somebody says theta is minus something, you will immediately interpret it as an anti-clockwise, sorry, clockwise rotation. So here you go. I think this is clockwise, and this is anti-clockwise. Anti-clockwise. Okay. Likewise, likewise. Mm, what about torque? So torque. Okay. So the way I do it is, so let's say that an object is rotating about this origin. I think I'm giving you a kind of thumb rule. Uh, Please note that I'm now focusing on the kind of problems that we're going to get into, which is, I keep telling you that the forces, I think it's worth repeating here, forces in xy plane and torques will either be something into plus k or something into minus k. These are the only possibilities. So please remember this, and that is in the z direction. So tau is only in the z direction. That's what it means. This whole statement just means that torque is only in the z direction, and the reason is this: the forces are only in the xy plane. Okay, so here we go. If I find a force like this, okay, now intuitively it's pretty obvious that this particular by the way, this origin is the pivot. Okay, so how do I mark it? This origin is a pivot of this pure rotation. I'm talking about pure rotation now. Pure rotation, that is our immediate concern. So here you go, the origin is a pivot, and here's a force acting on the scale. Now what is this force trying to do? So we have a torque that is clearly trying to twist the scale in the clockwise direction. So here's the torque. Now if you want, you can easily find the value of the torque. It'll be F into this distance, perpendicular distance, like it's going to be, let's say this is whatever, L. So in this case, there is Fl as a torque at that instant of time. But what I want to tell you is that this Fl torque will be given a minus sign. So this is the correct value of the torque at that instant of time, and the reason is that it's turning the object in the clockwise direction, and this is what my intuition says. And I think you'll get exactly the opposite story if the is happens to be a force in this direction. Let me call it F dash. In that case, the torque is again going to be F dash L, but this time it's going to be in the positive k direction is equal to tau. And the reason is that this particular force is actually twisting this object in the anti-clockwise direction. Okay, so please keep this in mind. This is what we will interpret the sign of the torques. Okay, so now let's redo this problem. This time I'm trying to keep in mind the sign convention. So let me try. So here it is. I'm going to say that I'll just arbitrarily assume that this position is theta is the origin, that is theta is equal to 0. Now it so happens that some instant of time the pendulum happens to be in some position, let's say an theta. And you can clearly see here that I'll just write it here that theta t is positive. And the reason it's positive is that from the origin we are going in the anti-clockwise direction. So clearly theta t is positive. Now let's just look at the torque at that instant of time. So what do I need to do? I need to draw the free body diagram. Now there are two forces on this object. One is the gravity, and the other is, please remember that the pendulum length is constant. Now there is a force called T on this object, and now I'm going to say torque due to T about the pivot point here, which is the origin, about the pivot is equal to 0. So there's no need to worry about T, but what is the torque due to mg? And here's the thing that now I'm using the sign convention. Okay, what is the sign convention? I think this mg is trying to rotate this in the anti-clockwise direction about the pivot. Okay, so about the pivot, this particular force, gravity, is twisting this object in the anti-clockwise direction about the pivot, and therefore the torque is going to be negative, and it's going to be mg into L sine theta at that instant of time. We have frozen everything, okay, in time, and we are analyzing it at that instant of time, and we are writing the equation. So here you go, minus mg, okay, minus, I'm not right, I can write k, okay, please note that I'm being extremely nice and careful, but the key point is that torque is negative. Okay, and what does the law say? The law says that this particular torque at that instant of time is equal to I into alpha, and we're done, by the way. But the only see, look at the use of this formula now. Torque is negative, so minus mg L sine theta is equal to the moment of inertia, which is I think we saw it last time, ml square into d square alpha by what am I writing? D square theta by dt square. If you want, you can write alpha. So this is the correct equation, and this time you will be very happy that I have followed the sign convention. So once again I repeat, torque is equal to I alpha. Now I'm going to use this equation, so I'm going to use the coordinate system. Okay, after using the coordinate system I use my sign convention, and the torque turns out to be negative because the forces are known. So mg sine theta t, and then I is of course ml square, and then alpha, which is the unknown, or that's what the law says. Let's call it Newton's laws. Sorry, d square theta by dt square. So this is the equation to be solved, and this time when you get the answer, you're going to interpret it in sign convention. Okay, so So I'm hoping that this clears up the sign convention part. Now let's do one thing. Um, let's go to the physical pendulum. So now I think I'll make it in the next video, but I'll just give you a quick intro. What is the objective? So physical pendulum, and I'll tell you what the objective is. There is a pivot, and this time it's a scale, a solid scale, which is doing its job by rotating about this pivot, and one can sort of intuitively know that in some sense it behaves like the simple pendulum. It will go back and forth when you leave it, and let's assume everything is frictionless. Now when this is happening, um, the what does the so basically one thing is obvious, that it's not a point particle, and but however we do have, but it is pure rotation of a system of particles, which is the scale, pure rotation of scale, which is a system of particles. Should I write it here? System of particles. And for this we have, for pure rotation, a beautiful equation which and okay, forces are in the xy plane. It's worth repeating this all the time. We only have forces in the xy plane, and there are and the motion is in the xy plane, and rotation about, okay, just tell you x, y, and remember that the axis of rotation is the z axis right here. Okay, z axis right here, meaning that right at the pivot point, and it never moves the axis of rotation. That's why it's called pure rotation. Yeah, that's why it's called pure rotation. And now we have the famous equation, tau is equal to I alpha, and but do we know anything more about this motion? So I'll let you know in the next video. I'm going to have one more nice equation, or maybe I shouldn't hold the suspense too much. In addition to this equation, I have one more nice equation which is valid at every instant of time. By the way, this is of course valid at every instant of time. At every instant of time, there is an equation that I don't want you to forget. Force external on the system, in this case it's just the scale, a system of particles, is always equal to mass of the system into acceleration of its center of mass, and this is also true for every instant of time. So we're going to freeze time, and we're going to use this equation and also this equation, and these are the two things we have learned. We're very happy with it. Now what is it that we'll be able to predict? What is it that we'll be able to predict? What is our prediction? And is it something that we are happy with? So let's look at that in the next video. Alright, see you. Bye.